Hey there, math fans. Dr. Andy Lovelace here. Going to talk about the derivation of the center of mass in Math 126. But before I do that, I need to give a little precursor on how we compute center of mass for just two people on a seesaw. There are my kids years ago on a seesaw. So this is a precursor. You can skip straight to the derivation, which will be in a separate video. But I want to go through this piece where everything starts. So imagine you have two people here standing on this seesaw with two different masses. And let's assume somewhere over here we call this x equals 0, and we'll call this x1, and we'll call this x2, their coordinates. So the question is, where would you put the balance point, assuming they're not the same masses? So usually in class I say, what if this person weighed more? Maybe this is me over here, a little bigger around. I would usually ask students, where would you put the balance point? Assuming that the seesaw itself doesn't have any mass. And you put it a little closer to that side. So we call that the fulcrum or the balance point. So there's a law that's been around for a long time called the law of the lever, which says something about this distance. And I always encourage students to go experiment if they can still find a seesaw on a playground somewhere, to find this length. So it turns out that, the things you observe is that when this one is twice as much as this one, this distance is twice as much as this distance. And that's the so-called law of the lever. And there's a lot of history here. Archimedes was one of people have studied the lever before that, but Archimedes said if I had a lever long enough, I could move the world. So anyways, the law of the lever, that's the thing we're going to start with, is this. M1 times D1 is M2 times D2. And that's really it. Everything we're going to do in calculus stems from this one observable fact. So then we say, well, what is D1? It's x bar minus x1. It's that distance. And that's going to be equal to this, x2 minus x bar. And I usually stop when I'm doing this in class and I say, here's an algebra challenge. Get x bar by itself. So it's a fun little, I give my students a head start. And then I say, all right, when I start, you have to try to be done before I do it. And we race through it. Move all the x bars to one side. And you get this nice kind of symmetric looking thing. Take a quick peek at my screen, make sure I'm not leaving something off. And then you can factor, the key step. And so you get x bar is m1 x1 plus m2 x2 over m1 plus x2. That's it. It's really an averaging formula or a weighted average. We call the thing on top a moment, or in physics they do, and we call this the total mass of the system. So it's this weighted average. And it really does make a lot of sense. I mean, if this is 10 and this is 5 and this is 2 and this is 20, it says what you need to do is multiply. So 2 times 5 plus 20 times 10. And we're going to divide by the total mass of the system, which is 5 plus 10. And yeah, I just made up these numbers, but let's see what happens. We're going to get 10 plus 200. So 210 divided by 15. Why did I make my life hard here? Well, you can divide top and bottom by 3, so it's going to be 70 over 5. And then you're going to get 70 over 5 is 114. And if you put 14 here, hopefully it works out as I'm expecting, this is 6, and this is 12. Twice as much. Okay, so there's that law of the lever in action. So the reason I show that is really everything stems from that, even if we're going to do center of mass for more things. And here is how you can jump it up a level. So imagine now a third person steps onto the scale, so to speak. So what we do when we add more people, it's this inductive reasoning idea, which is assume now we have one giant person standing there, and the mass of that giant person is m1 plus m2. And then let's pretend these people are gone. So we've morphed those people into one person. And then imagine someone comes up here and stands right here, and they have m3, and this is x3. And now we want to balance those two people. So you can do the same thing. You could say, well, let's pretend this is my x. My new, whatever we want to call it. What would be a good notation? x1, 2. And then we're going to find a new x bar right here. And so you can do all the same thing. The distance from there to there, the distance from there to there. You can solve for x bar. And x bar is going to be the mass of the first thing, which is m1 plus m2 times this x12 bar, which is this thing we just figured out. And a cool thing happens when you insert that there. Plus, you're going to have m3x3. And then you're going to divide all that by m1 plus m2 plus m3. And when you plug this thing in, you'll see that those two things cancel. And you get the exact same formula with 3. And then you can go from 3 to 4. And you can go from 4 to 5. So you get this general formula that x bar is m1 x1 dot 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 plus mn xn. And you can balance a whole bunch of people on a seesaw if you know all their masses. You can know where the fulcrum is before they even stand on there. Okay, so that's the precursor. That's the starting formula for where we do the calculus, because we're going to go from a finite number of points to an infinite number of points. All right, I'll do that in a separate video.